All right, so several things that we've got going today. So I want to talk about Lab 6 first of all, because that's due today. And I think there's probably some questions because I've only signed off on 2 Lab 6s so far. And then I want to go back and talk a little bit about some aspects of Lab 5, which was graded last week, and you've got feedback on that. And then we can talk about homework, and there's probably some questions on the homework. Lots of questions, good. And then we're going to continue talking about state machine analysis. And my goal for the most part today, we've been going through a lot of stuff, right? And how many people here feel like since the midterm things have kind of gotten really crazy as far as pace and new material and so on, right? So, and this is the nature of the course, because the first half of the course is in a lot of ways it's sort of the same things we were doing in 120 chapter 5. It's more advanced, there's product of sums and so on, but it's the same basic material we're working with, combinational circuits, and then all of a sudden, bam, we start talking about these sequential things and flip-flops and memories. It's a whole new game, okay? So today in particular, rather than going over new material, I want to really concentrate on what we've been doing post-midterm, okay? Which means going through the homework in particular, and then probably doing some practice on the board with some state machine analysis. Okay, so I want to get everybody on a good solid footing for that. And then Thursday or possibly next Tuesday, we'll go into state machine synthesis. And we'll learn how to work things in the other direction. Here's a system I want to build. How do I go about designing it? Okay, but that's easier to do once you've done enough practice with, here's a circuit that's already been built. How do I figure out what it does? Right, so the analysis section is usually a little easier, and it helps you get into the synthesis aspect. And then we're going to toss all that out the window later on next week and go into something totally new, which is Verilog, which is where we'll learn sort of the more modern way to do everything we've been doing for the past several weeks. But that'll build on everything that we've done so far. But that'll give you a flavor of sort of what you're going to be doing on a daily basis as an engineer, if this is the direction you're going. So that's our general plan. So let's start with Lab 6. Questions on Lab 6, traffic light with delayed yellow light built in. So how many people have finished this? Okay, good. Did you implement it the way that we were describing with the delay circuit and combining the original and the delayed signal? Figuring out, okay, good, that's good. So no other questions about that? Okay, so catch me in lab hours if you're having troubles with your circuit and you want to go over it. We can definitely do that, or catch whoever's working in there. I'd like to go back to something from Lab 5. So Lab 5, you were doing the blinking lights, right? So you had 8 LEDs and they were blinking in a sequence. And this is from the data sheet for the 7493, the counter chip. And I want to point out something in here. This is what's going on internally. Okay, this is a picture of how the chip is actually built inside. And I want you to notice something. There's this output here, QB, that's one of the outputs available from the chip. But where does it go? It goes into the clock of another one of these flip-flops. And the output of that flip-flop goes into the clock of another flip-flop. So I want to look at what this does, and then I want to tell you why you don't want to do this yourself. Okay, but let's see what this does. So what kind of flip-flops are these? JK, right? There's a J, there's a K. It's not showing us what the values for J and K are. There's no inputs here, but they're effectively being treated as if they were both 1. Okay, in general, when you have an unconnected input in a picture like that, we can be pretty sure that it's a 1. So let's look at the behavior for a JK flip-flop. And I'm using Q bar to show the new value of the Q output after the clock ticks. So if J and K are 0, do you remember what the new value of Q is going to be? Yeah, it's whatever the original Q was. It doesn't change, right? This is the do nothing state. Okay, what if K is 1 and J is 0? You've got at least a 50% chance of guessing right.
0.
0, excellent. Okay, this is the reset state. Now you got a better than 50% chance on the next one. What if
1.
J is 1 and K is 0? There you go. That's a 1. Okay, now here's the one that's really hard to guess. What if J and K are both 1?
Q bar.
It becomes Q bar. It acts like a toggle flip-flop. Okay, so if Q is currently a 1, tick the clock, it becomes a 0. Tick the clock again, it becomes a 1, and it just keeps changing between those two values. So inside the 7493, we've really got 4 toggle flip-flops that are permanently set to just keep toggling the output. Every time that this clock ticks input B, this output's going to change. So let's see what this circuit does. And as I suggested in discussing this lab, ignore input A and QA. Let's just look at these 3 outputs. And we have a clock going in here. So let's suppose that initially all of these things are 0, all of these outputs. And let's just look at what happens each time that this input B, this clock, which was coming from your 555, each time it ticks. And each of these, remember, these are T flip-flops. They're going to toggle whenever the clock changes from a 1 to a 0. Okay? And it's a 1 to a 0 because there's a little circle right there. So these are negative edge triggered. Okay, so flip-flop toggles when the clock drops. So suppose all our outputs are 0 to begin with. Does anything happen when input B changes from a 0 to a 1? Positive edge. No. What happens when input B changes from a 1 to a 0? Something will happen. Well, what's input B connected to? It's the clock input on a toggle flip-flop. So when the clock drops on a toggle flip-flop, do you know what I mean when I say the flip-flop toggles? It means the output changes from 1 to a 0 or from 0 to a 1. So it goes high. So QB, which is the output of that, is going to go high. And that's feeding the clock input on this flip-flop. Now when the clock input goes from 0 to 1, nothing happens, right? So nothing changes here. QC stays the same. And since QC is connected to the clock here and this clock hasn't changed, nothing changes there. So the first falling edge of the clock, we change basically from a value of 0, 0, 0 to 0, 0, 1. Well, what happens on the next clock tick? What happens in this flip-flop next time that our clock drops? QB goes to 0.
QC goes to 1.
So the clock going into JK just counts as a 1, 1 or a 0, 0?
The clock going into
The B going into C.
this?
The B going yeah.
So whatever the value, so in this case,
That's J and K.
J and K are 1. Okay, that's what's making this thing act like a T flip-flop. The only thing that's being changed here is the clock. And the clock is whatever this output QB is, right? So in this first row, QB was 0, this input B, the clock ticked, QB changed to a 1. So this clock input changed from a 0 to a 1. Doesn't do anything.
Right.
But now we drop this input B again, QB changes from 1 to a 0. So now this clock is going from 1 to a 0. So what happens there?
So C into a 1.
Changes QC into a 1. And that changes this clock to go from 0 to 1. But that doesn't affect anything, right? Because this is all negative edge triggered, so this is going to stay a 0. But now it's counted to 2. And we can do this one more time. Input B drops. QB is going to toggle. Well, this is just going to keep repeating, right? Every time the input drops, QB is going to toggle. There's no two ways about that. So QB is going to become a 1, which again means this clock input on this flip-flop is going to go from 0 to 1, doesn't do anything. So this doesn't change, this doesn't change. But one more time, and this is where the good stuff happens. Input P drops. We know QB is going to toggle. What's that going to do when QB goes from a 1 to a 0?
Drop C to 0.
Changes QC to a 0. What does that do when QC changes to a 0? Yeah, that toggles QD, so now QD becomes a 1. So this is how your counter was counting. It was really 3 toggle flip-flops with each output feeding the clock of the next input, the next flip-flop. And so it counts 0, 1, 2, 3, 4, and you can work through it and it'll count all the way up to 7, and when it gets to 1, 1, 1, and you do one more input from your 5, 5, 5, QB will toggle to a 0. That changes this clock from a 1 to a 0, which toggles its output. And when this changes from a 1 to a 0, that toggles QD, and you go back to 0. So this is one way to make a counter. If you have nothing in your parts box but wires and T flip-flops, you can make a counter. And you do it by taking the output of one and feeding it into the clock of the next. And it works, but it's a poor design. If you remember why it's a poor design, I said something last week. I said a lot of things. Don't mess with the clock, right? That was the golden rule. All the clocks get fed from the same thing, and you don't monkey with that signal. Okay, the reason being because these state machines that we're analyzing and we're going to start building depend on the fact that everything happens in unison. And if we have a clock going over here, but that clock runs through some circuitry before it gets over there, stuff is going to happen here before it happens over there, and it's not synchronous anymore. And now you got a design nightmare, right? So everything that we're doing from here on out works well because all these clocks happen in unison. That's the idea of a clock, right? It's like if every clock in every classroom showed you a different time, we'd have a really big problem, right? So we want to keep these clocks as clean as possible. And clocking is a whole subdiscipline. You can do a PhD just on clock design for computer architecture because it's such a critical piece of the system. And in a modern CPU, the clock goes everywhere. There was a processor in the mid-'80s, it was called the VAX Alpha. And when people would talk about it, they'd sometimes talk about the 2-foot hot dog. Okay, so this was a chip, right, an integrated circuit. It was small, you could fit it in your hand. But the clock line, if you were to take it and unfold it and stretch it out, it was supposedly 2 feet long, right? But it was all bundled up into this roughly hot dog looking thing for the purpose of making sure that the clock signal got to all the different parts of the system at the same time. Because we're talking speed of electron propagation, and this may not seem like a big distance, but if one clock signal has to go this far and the other one has to go this far, that can be a big difference in time. And if you're trying to run things at a gigahertz clock rate, that might be a critical difference. So clock distribution, whole discipline into itself. So don't mess with the clocks, but if you really need a counter with some T flip-flops, you can do that, right? It's not like a sacred law, but it's a guideline for making circuits that are easy to analyze and debug and make work properly. Okay, so that's what's going on inside the 7493. So let's switch gears and let's talk about homework. And I sort of threw all of the chapter homework at you, except for question 2, I think, and said go ahead and take a shot at it. And the usual exercise, if you have a lot of good questions about the homework indicating that you put a lot of effort into it, right, then I will probably let you turn this in on Thursday instead of today. Yes?
So for 6 through 11, one thing that I found difficult was that the nodes are not clearly identified.
The nodes.
So it's hard to know if you have the right equation.
Let's see.
Yeah, I had that same. That's why I didn't.
Oh, you mean the connections?
Yeah.
Yeah, that is a problem.
So
But here's a way you can figure this out. You can only have one output driving things. You can't have outputs connected together. Okay? You can have one thing feeding multiple inputs, but you can't have an output with something else driving that output. Okay? So for example, and this one's not too bad. Let's go to this one's really confusing, I think, right? Where the heck does D2 come from down here? Well, it can't be coming from the inverter because this is an input to the inverter, and D2 is an input. And if it was connected to this line, there'd be a dot right here, right? And if it was connected to this line, there'd be a dot. But if things are meeting in a T, we don't need a dot, right? Because there's no option. It's got to be a connection. And if we follow this particular path, we find the output of this OR gate. Someone back there said it. So this is generating an output here. It's feeding the input of the inverter, and it's also feeding D2. So D2 would be equal to the OR of, well, this comes from Y1. And the second input, well, it can't come from here because that's an input. Let's trace it down. Oh, there it is, Y2. So the output of this OR gate is Y1 or Y2, so that's what D2 is equal to. Does that make sense? So if I were to draw this, I would put some big dots where I wanted those connections just to make it more clear, for example, that there's no connection here. But some of them take some chasing around, and especially these last ones, it can be a challenge, right? So where does this input come from here? Well, it's got to be coming from that AND gate. Yeah?
So I'm assuming from 6 through 11, when it says to make a state diagram, you would have to go through the entire process.
Yes.
And so I guess I'm having trouble with making the state transition table.
Okay.
Figure out exact what, how you do it.
Okay, so we're going to talk about that. We're going to go through an example, and then you're going to go to the board in groups, and we're going to work on a bunch of these problems together. Okay, so we'll come there shortly. Yeah?
So I guess for those problems, I was finding the equations and then identifying the states, and then after that, I was just having trouble making the table itself.
Okay. So was that a common difficulty?
Yeah,
Okay.
I rewatched your video 3 times.
Okay.
I did it, like step by step, and I still couldn't like memorize.
Okay. Yeah. So I made you some cheat sheets to take up to the board to work with. So this outlines the steps that we went through last time. And let's just go through an example using this as a guide, and then we'll split onto the board maybe and do this in groups. But let's pick on a problem. I'm not going to pick on the funnest problems. Let's pick on.
So if we're using different flip-flops, is that going to change the way we do the problem or what we consider?
It doesn't change the steps that you're going to follow, okay? But here's the thing. So decide how many states you have. Okay, let's just go through this. Decide how many states you have. You've got 3 flip-flops, 8 states. 2 flip-flops, 4 states. 100 flip-flops, 2 to the 100th states. Okay, so just 2 to the number of flip-flops. Make a state assignment table, name your states, and choose what combination of flip-flop outputs you use for each of the states that you've named. Okay, that's just to give you something to use when you fill out your table. Write equations for the inputs to all the flip-flops in terms of the flip-flop outputs, and if you have an external input or inputs coming in, right? So write your equations so that you can stop staring at the diagram. Okay, you can just work with Boolean equations. And then making the state transition table, what you're going to do is when you get down here, list the next values of Q outputs based on the flip-flop behavior. That's going to depend on the type of flip-flop. Okay, if you have a T flip-flop, you're going to look at the T input. If it's 1, your Q is going to toggle. If it's 0, it's not. If you have a D flip-flop, if D is 1, Q is going to become 1. If D is 0, Q is going to become 0. If you have a JK flip-flop, who the heck knows? Depends on the value of J and K and the current value of the flip-flop, right? So that's where it's going to come in, is when you're filling in these new values of Q, which is sort of the last columns in the transition table. And then once you have the table, you make a diagram from it, and that's kind of the fun part, because then you can toss the big long table and you just got a nice picture. And you stare at the picture and you can figure out, oh, this thing is predicting weather, or this thing is telling me which class I should go to next, or whatever. So can we pick on the solved problem? Because the book gives you a solution to this, but we can follow this guide and come up with our own version of the solution. So how many flip-flops do we have? 2 flip-flops, and what type of flip-flops?
DR.
Oh yeah, they are DRs, aren't they? That's weird. So we haven't really talked about this, but you notice that both of those R's, they're connected together and they go to this thing called CLR. That means clear. So what we'll see, especially when we're synthesizing machines later this week, what we'll see is that sometimes we're not using all the possible states. We know with 3 flip-flops we could have 8 states, but maybe we only needed 5 states. So we may have 3 states that we never use. And if we're trying to do an efficient design, we may not worry about those 3 states. We may say, I don't care what happens if you're in that state. It's never a state we're going to be in. But what if you power up your circuit and you happen to be in one of these states that you didn't plan on? So you put something like this into your circuit. This is a clear. And if you drive this signal, what it's going to do is force both of these to zeros. So it's going to basically put you in state 0, 0. And it lets you begin the system in a known state. This is the big reset button on your piece of equipment. So that when you power up, things aren't working. Or if something goes wrong, an alpha particle comes down from the sky and it trips up your logic, pop the reset button, you're back to a clean start. So a lot of different kinds of flip-flops have this reset. Sometimes it's called clear. And if you assert that signal, then it forces the flip-flop to a 0. You also find devices with a preset input. And if you force that input, then it sets the value to a 1. And there's varieties of these. Some of them will happen as soon as you assert that signal. Some of them it will happen only if that signal is asserted and then you tick the clock. So that former case, that's called an asynchronous clear. Means as soon as I set that clear line, flip-flop gets cleared. Doesn't matter what the clock's doing. A synchronous clear input, I would assert the clear line, and then when the clock ticks, it clears the flip-flop. And you can buy devices of both types. You can buy them with an asynchronous clear and a synchronous preset. There's different versions for different applications. So for us, we can mostly ignore that and just know that when that signal is asserted, both flip-flops are going to go to a 0. So this is really a D flip-flop, but it's got this clear input, and it doesn't tell us if it's synchronous or asynchronous, but it doesn't really matter. All right, so we got 2 D flip-flops. So how many possible states do we have?
4.
4 states. Okay, decide how many states you have. That's 4. Name your states and make a state assignment table. So what should we call our 4 states? Say again?
A0, A1, and
We did that last time, and I went ahead with that because I wanted you to know the state names aren't precious, but I don't want to confuse people
ABC.
by doing that again. Okay, let's do A, B, C, D. And we're making a table of state versus the Q output combination. So let's look at our picture again. We've got two outputs, Q1, Q2. So Izad calls these Y1, Y2 in these questions. We can call them whatever we want. Okay. I'll go ahead and use Q1, Q2 just to be consistent with what we've done so far. But if you prefer to use Y1, Y2, that's fine. They're exactly the same thing. It's just two names for the same thing. So the flip-flop outputs, right, these are the Qs. And what we want to do is list all the possible combinations. And for each combination, we're going to have a different state. And there's nothing magic about how we make this assignment. I could say that A is 1, 1, and B is 0, 0, and C is 0, 1, and D is 1, 0. Doesn't make any difference. Well, it changes everything, but other than that, it doesn't make any difference. Right? You'll get the same behavior in the end. So I'm a creature of habit, so I'll just put them in sort of the usual ordering. And for me, I would do Q2, Q1, okay? But just to show you that it's not precious, we'll leave it Q1, Q2. Okay, this is just so that we can talk about state A instead of state Q1 equals 0, Q2 equals 1, right? It's just a shorthand. All right, so we've made a state assignment table. Next we have to write equations for the flip-flop inputs in terms of the outputs and any external inputs. Well, we have no external inputs going in, right? Clear doesn't count as an input. It's just driving the reset on these flip-flops. The clock is never considered an input. An input would be something like down here we've got an X coming in. Okay, but up here there's no external inputs. So we just want to write the equations for the inputs, D1, D2, in terms of the outputs, Q1, Q2. So who can write an equation for D1? Yeah, Y2 goes through an inverter, and that feeds D1 directly. So D1 is not Y2. I'm going to call it Q2, but it's the same thing. So I'm going to say D1 equals Q2 bar.
Yeah, those two things kept screwing me up too.
The Q's and the Y's?
I found myself interchanged.
Yeah. And they're not different, but if you
Yeah,
use them
they're the
both,
same thing,
it
but
starts
then you
getting
look at it like,
confusing.
why did where'd Y come from?
Yeah. All right, what about D2? D2 is just Q1. It's just a wire. All right, so there's equations for the flip-flop inputs, and then write equations for any outputs also in terms of the flip-flop outputs. But there's no output specified for this circuit. So sometimes you'll have some more circuitry over here, and you have usually they're labeled Z1, Z2, right, coming out of this whole system. We don't have any of those to worry about. So we're really done with step 3. We wrote our equations. We're done with that picture. Okay, we don't have to look at it anymore. So this and this tell us everything we need now to make our state transition table. All right, so 1 row per input and state combination. We have 4 states. We have no input, so we're going to have 4 rows in our table. If we had an X input, we'd have 8 rows in our table, right? 4 states and 2 possible input values. So list the current Q output values for a given state. Okay, so we want to know the inputs and the state. So I'm going to start off with present state. And this can be A, B, C, or D. And list the current Q output values for the given state. That's just reading from your state assignment table. So if we're in state 1, what are the values of Q1 and Q2? 0, 0. If we're in state B, Q1, Q2 are 0, 1, and so on. So you're basically just copying this down here. Okay, but we want everything in this one state transition table. All right, so we've got the current Q output values for each state. List the corresponding output values. We don't have outputs. If we did, we'd have an equation like Z equals Q1 or Q2 bar, and we put a column for Z, and we'd write down Q1 or Q2 bar's value in each of these rows. But we don't have outputs here. Okay, fourth step, list the flip-flop inputs. Well, we have two flip-flops. They each have a D input. So here's D1, here's D2. And we can fill these in because we've got equations for D1 and D2. So we already decided D1 is just the complement of Q2. Yes?
So for the D1 and D2, if it was another type of flip-flop, that would be like the J and the K or the S.
Exactly. If we have a JK flip-flop, we'd have a J1, K1. If we had a T flip-flop, we'd have a T2. If we had another JK, it would be J3, K3. Right? So whatever the inputs are for your particular flip-flops, you want to list all of those here. And you should have equations already for what each of those are in terms of Q1, Q2, and any inputs. So now we're back to a week 1 exercise. Here's an equation. Let's write a truth table. So D1 is Q2 bar. So what are the values for D1 from top to bottom?
1, 0, 1, 0.
1, 0, 1, 0. Does everybody see that? Okay, someone else. What are the values for D2 from top to bottom? 0, 0, 1, 1. Because D2 is just whatever Q1 is. All right, so we're just building a big truth table here. All right, now here's possibly the trickiest step. List the next values of the Q outputs based on flip-flop behavior. So we got to know what these flip-flops do. So let's make a table for a D flip-flop. And remember, we're only interested in what happens when the clock ticks. So if D is equal to 0, what's the new value of Q after a clock tick?
0.
And if D is a 1, it's a 1. Right? That makes D flip-flops the simplest ones to work with. The output just matches whatever the input is. Okay, so our goal here in step 5, list the next values of the Q outputs. So we're after Q1 plus and Q2 plus. And do these one at a time. Let's just look at flip-flop 1. So the current value of flip-flop 1 is a 0. The D input is a 1. What's the new value going to be? This doesn't matter, right? The current value of a flip-flop has no effect on its new value. That's another reason why they're easier to work with. The only thing that matters is what the D input is. So in this case, the D input is a 0. What's the new value of Q? 0. There's a 1, there's a 0. And now if we just look at D2 and Q2, if the input's a 0, the output's going to become a 0. If the input's a 1, the output's going to become a 1. So when you do this with D flip-flops, what you realize at some level is this is just a copy of that. We're just taking D1, writing it down as Q1 plus. Okay, but that's only for a D flip-flop. And we're not doing that because the procedure says copy these columns over to here. We're doing it because the procedure says list the next values of Q outputs based on the flip-flop behavior. And that happens to be what a flip-flop does if it's a D flip-flop. Okay, so don't get tricked into thinking there's a shortcut here. Right? And the more you do this, the more you're going to internalize what these flip-flops do. And by the time you've done a few of these, D flip-flop, JK flip-flop, they're going to be second nature to you. Right? And that's important because then you don't have to think too hard about how to use those things. So this is more than just getting you a state transition table. It's brushing up on everything we've done, right? Truth tables, Boolean equations, all of that stuff. All right, so we've done the hardest part now. We've filled in these new values of Q. So the last step here is list the next state based on those next Q outputs. So we go back to our state assignment table. Suppose Q1 is 1 and Q2 is 0. What state are we in? We're in state C. Suppose both are 0. What state are we in? We're in state A. Both 1, we're in state D, and a 0, 1 for Q1, Q2. 0, 1, we're in state B. So this is our next state. That's your whole state transition table. And what it's telling us is really, if that's your present state, this is your next state. All this other stuff is just getting us from here to there. The information we want from this table is really, if I'm in state A, my next state is C. If I'm in state B, my next state is A, and so on. So now the last step, draw a state transition diagram based on this table. So let me just sneak it onto the bottom here. So let's write down some states. And it's telling us if we're currently in state A, when the clock ticks, our new state is going to be C. If we're currently in state B and the clock ticks, our new state's going to be A. So we transition like that. If our current state's C, our new state's going to be D. And if our current state is D, our new state's going to be B. And now it's really easy to see what the system does, right? It's got 4 states, whatever that means, but each time the clock ticks, it goes from A to C to D to B, and then back to the first state A. And it just runs between these 4 states over and over and over again. So it's something like a counter, right? Except we're not really counting in numbers, we're counting A, C, D, B, A, C, D, B. And that's probably not at all clear from looking at this, right, that that's the behavior we're going to get. But we've reduced it to a very simple visual representation of how the system flows from one state to another. So it actually has 4 states, and it goes through all 4 states every 4 clock ticks. Yes?
I guess one thing I'm finding confusing about flip-flops is like when you have their characteristic tables and you have their excitation tables, how those two work together, if they're different, and like
Okay, so I've avoided using those terms, and I know they're in the book, right? And I want you to look at the book. So
when you tell us we're going to know the tables by heart, like which ones do you want us to know?
So this is the most important, okay? This is how the flip-flop responds. Okay, if the D input is 0, Q becomes 0. If the D input is 1, Q becomes 1. And let's spec that out for our different flip-flops. And then let's talk about what else we can get from those. So a D flip-flop. The new output's whatever the D input is. Okay, a toggle flip-flop has a T input. So if the T input is 0, you're saying don't do anything. Ignore the clock, basically. So if the T input is 0 and the clock ticks, the new value of Q is whatever the old value was. If the T input is 1, you're saying I want you to toggle the value every time the clock ticks. Bounce back and forth between 1 and 0. So the new value of Q will be the complement of the old value. A JK gives us the opportunity to do both. Right, so 0, 0 is a no-op, 0, 1 is a reset, 1, 0 is a set, and 1, 1 takes on the toggle behavior. Okay, if you know these tables, you know everything there is to know about the flip-flop.
About the SR.
We haven't really talked about an SR, and an SR is really a JK without this fourth stage. So let me do this in parentheses in a lighter color. So 0, 0 is a no-op, stays at Q. If R is 1, that's the reset state, forces it to a 0. If S is 1, that's the set state, forces it to a 1. 1, 1, we consider to be an illegal stage, just like with an SR latch. So this is really a subset of a JK. It's a JK without this added benefit of acting like a toggle. So we don't really use SR flip-flops much.
When would you decide to use an SR? Kind of seems
Probably on a
like you do
test
it
question or a homework
all
question.
that's the only reason.
Yeah, I mean, I've never used one. I don't even know if you can buy them. Yeah.
So when you're saying that it's forcing it to a certain 0 or 1, are you looking at the value that's currently high, or for like the S and the R? So when you're looking at what Q should be,
Mm-hmm.
how do you know if you need to look at the set or the reset?
You look at both.
Okay.
So let's. Do you want to do SR or can we do JK?
Doesn't matter.
Okay, let's stick with JK. So let's do a timing diagram. So we'll put a clock out here, and you have some timing diagram homework questions with some other aspects to them. Let's just see what this does. And I'm going to suppose that Q is starting off at a 0. Okay, just to make it a little more interesting. So remember, nothing matters except when the clock ticks. And other than when we looked at that 7493, we're always looking at positive edge triggered, unless we say otherwise. Yeah?
I mean, the only thing different about negative negative edge is it's just because it's on the end.
Yeah,
There's no
negative
other-
edge would pay attention right here and right
So
here.
it'd just be the same, but at that spot.
Yeah,
No other-
exactly.
Anything different in it?
Nope.
Okay.
It's just, and you always get to choose, and you can buy positive edge triggered devices, negative edge triggered devices. And if you have a positive edge and you want a negative, just run it through an inverter before you feed any of the clocks, right? But we're not supposed to tinker with the clock, so get a negative edge triggered device. All right, so suppose Q is starting off at 0. The clock ticks here. J is a 0 and K is a 0, so let me write these in. J is a 0, K is a 0. The new value of Q is whatever the current value is. Q right now is a 0, it's going to stay a 0. Okay, when we get to this clock tick, J is a 1 and K is a 0. Did anything happen here when J changed? Absolutely nothing, right? Because it only looks at things when the clock ticks. So J changes to a 1, everything's still stable, but here the clock ticks. J is a 1, K is a 0. What happens to Q? It becomes a 1. And it's going to stay that way until the next clock tick. And here, J is a 1, K is a 0. So what's Q going to be after the clock tick? J is a 1, K is a 0, Q is going to be a 1. And it's going to stay that way until over here. Now here J is a 1 and K is a 1. So the clock ticks, what's the new value of Q going to be? Does everybody see that? J and K inputs are both 1. A JK flip-flop will toggle its output. Currently Q is a 1, so on this clock tick Q is going to become a 0. And if we did one more of these, so here's another clock edge. And at this point, still J is 1 and K is 1. What's Q going to do here? It's going to toggle up to a 1. Okay, so that's what that JK flip-flop is doing with those particular inputs. Does that make more sense?
So how do you know when you have to factor in the setup time and the hold time?
Ah, now that's another question. So there's a homework question on that. It asks you to draw some windows around these. So we get to fortunately ignore that for the most part. Okay, all these questions that say analyze, draw a state transition diagram, things like that, we're mostly ignoring setup and hold time, or we're assuming that the clocking is done reasonably well. Okay, but in practice, right, if I had risen this edge right before the clock tick, the system might misbehave. So we need to know that this input is stable for a certain amount of time before the clock tick. Do you remember what that time is called? That's the setup time, so tau SU. And we're not allowed to change it until a certain amount after the clock ticks. That's the hold time, so tau H. Now suppose you were actually building this circuit. You were actually going to use this to make a soda machine, right? And you've got to choose how fast is my clock going to run. Well, if your clock takes 5 minutes per clock tick, someone puts in their coin, it's going to take 15 minutes before it tells them they put in 25 cents, right? So you want a fast clock, but how fast can you make that clock? Is there no limit to it? Could we run a clock at 100 terahertz? Probably not. Well, yeah, there'd be a lot of heat, so our sodas would be warm. The other problem is, right, these flip-flops have maximum speeds they can run at because of this setup and hold time, right? We have this circuit over here. When an output changes, it's got to take time to get over here, go through this inverter, come in here. It's not going to immediately go into D1. It's going to be delayed by the propagation delay of whatever circuitry you have. And if you have a big circuit like this, right, or a really big one like this, there's a lot of propagation delay. So setup and hold time will come into play when we say, hey, how quickly can we clock the system? We basically need to know what the minimum setup time is, what the minimum hold time is, and make sure we don't clock the tick anywhere between, don't tick the clock anywhere between here and here. So if the time here and the time here adds up to 10 nanoseconds, the fastest we can clock the system is where a clock tick doesn't occur any sooner than every 10 nanoseconds. And we're down to 100 megahertz clock already. If it's 100 nanoseconds setup and hold time plus all the propagation delay, we can't click faster than 10 megahertz. Okay, so there's a homework question there. We can work through the details of that after a break. Yeah?
Sorry for all the questions. So you
Questions
have
are
a
good.
hold-up time, a setup time, and a propagation delay, so technically that range is going to be even bigger.
Yes, because remember the general picture of our state machine. We have memory. We have logic. Memory goes into the logic feeds back into the memory, right? The feedback makes it a sequential system. So there's a limit to how quickly we can change the inputs on this. And there's also a time that it takes for inputs to the logic to turn into valid outputs. So we'll run through that problem in detail after break and see how those numbers play out. And it's mainly going to be the setup time and the setup time and the logic time. And the hold time kind of gets overwhelmed by those.
I have a quick question on the homework.
Okay.
When we do the analyze, are we also supposed to be doing put the the outputs, like Z1, Z2?
Yeah, so if you have outputs in here, then you want to include that. It's one of the earlier steps in here. So write equations for the flip-flop inputs and also for the outputs, okay, in terms of the Q values and the external inputs.
So when you put those in, what's the, I guess when you get the equation, what are you putting into that too?
So you're going to use that equation to list the corresponding output values in your transition table. And then I'll show you after break where to put those in the state diagram.
Okay.
There's a specific place to
That was
list
one thing I
those.
had no idea.
But the goal will be to, when you come up with this state diagram, be able to say like, okay, we're in state A and the output is 0. And then we go to state C and the output is 1, 1. Then we go to state D and the output is 1, and so on, right? So, and we'll talk about how to put those in. All right, so let's cool our brains. Let's take a 5-minute break, come back at 1 o'clock. And we're going to start by having people break into groups, go on the board. We'll work through some state tables, and then we'll go through more of the homework after that. Sound good? All right.
So when you join-
Professor.